So, good afternoon, everyone. Today is the last session of the Chemical Process Technology 2024, and today we'll be discussing all the uh, lectures that has taught, like from 43, almost the 43 lectures. We'll be discussing around that. We'll be uh, revising the old questions and doing some new questions. I'll be starting in 2 minutes. So let's start. Let me share the screen. I hope my screen is visible. So, this is the first chapter. So, this is the very introduction of the chemical process technology. So, first, this is the disciplines of chemical process technology. Then comes the level of education. That is the first independent level. That means the thermodynamics is independent. Then comes the physical transport phenomena, kinetics and catalysis. That is the micro nano level. Mesoscale means the particle and interfacial technology. In the reactor concepts and unit operations comes in the macro scale, and the industry or design technology and operation, all of these come in the scale up section. Next comes the basic flow sheet of macro process design, and in the meso process design, particles, reactors, reactor selection and design comes, and in the micro nano section it sites, molecules and intermediate kinetics come. This is the space and time scales. So reactor size is 1 kilometer, then plant size is 10 cube. Okay. Then drop particle is 10 to the power minus 3 meter. That is 1 millimeter. Electron is 10 to the power minus 12 meter. Okay. So that is how This is the space-time scale reaction, and along with the molecular vibration happens in this range of time scale chemical reaction, chemical technology occurs. Next come the process intensification. So one can be the petroleum geochemistry, then it can be the biochemical process, then the industrial catalysis. So commercially attractive catalytic reactions are required. The reaction rates mm, are to be known. Then the reasonable size reactor, the design of the reactor, and physical space and economic constraints are also to be taken care of. This is the catalyst, heterogeneous catalyst. We will be discussing this in later also. So it is a general chemical process structure where the raw materials is there, then the physical treatment happens, then the reactor, in the reactor actual reaction happens. After in the downstream process, this is separated, the unconverted raw material is returned back and or recycled back, and the product is separated through distillation column or absorber, and that is how a chemical process industry works. So this is the unit of the typical process, chemical process unit. Here are the module contents. Will be what Sarah taught in further lectures. Okay, so this is done. Next. So module 2 is about the structure of a chemical industry. Okay, so here you can see that in organic chemicals include sulfuric acid, sodium bicarbonate, then organic chemicals, synthetic dyes, crude oil, etc. Then what is required in a chemical industry, structure of a chemical industry, the specialty chemicals, the heteroatoms, acetic acid, formaldehyde. Between the base chemicals, there are mostly methanol. Okay, so this is about the sulfur. Then fossil fuel reservoir. So coal has the high production ratio, reserves to production ratio, then the gas, and then the oil. So this is for the energy production. Energy required by 2050 is the natural gas, oil, coal, and biomass. So what is biomass? Biomass will be replaced. Fossil fuels will be replaced by the biomass because it is economically sustainable. So here they have shown the what is the contents of the lignocellulosic biomass. Then comes the dissolution of lignocellulose, how the cellulose, hemicellulose, and lignins are separated. Then comes the properties of monosaccharides, disaccharide, and the enzymatic hydrolysis. Okay, so this is the gist of the second chapter. In the third is all about safety and loss prevention, because the chemical process reactors are very risky due to the kind of reaction happens, the hazardous compounds are there, the chemical compounds are there. So because of that, safety is a very much important factor in a chemical industry. So that is taken care of in this section. So you have seen safety issues is under what comes fire, explosion, toxic release, then the flammability. So you have to know the flammability limitations for every compound you are using in an industry. So these are the basic knowledge you should have before starting a process or starting a reaction in a reactor. Otherwise, disaster will happen. So you know about the Flixborough disaster. This is a nitrocaprolactam facility, and what happens? Cyclohexane produce cyclohexanol. Okay, partial oxidation of cyclohexane produce cyclohexanol. So what happened? He was like lost when a temporary conduit bypassing an out-of-service reactor burst into flames, leading to the loss of an estimated 30 metric tons. Okay, an unknown source ignited the vapor cloud. So bypass did not happen and it just got burst. And that is why spread throughout the factory. Okay. Insufficient cause. What was the cause? Insufficient support of the bypass pipe and a faulty design that failed to account for the movement of the pipe owing to the pressure. So it is very important to know what is the safety parameters of all the chemicals, what is to be done, and how to control a big disaster. What is the you have to know the proper design of a reactor, everything. Next comes the Bhopal gas tragedy. You know, this is the use of methyl isocyanate, a very toxic intermediate molecule. So this is the tragedy you know happened in India. So this is the phosgene reacted with an ammonia produces MiC, and then MiC with naphthol produces carbaryl, right? This is the conventional route, and this is the alternative route. Last one is the Seveso accident. So this 1245 tetrachlorobenzene reacted with sodium hydroxide produces 245 TCP, and it is a rapid exothermic process, so it got changed to TCDD, and this TCDD is released to air, and it is usually very toxic, and it has the dioxin is carcinogenic of TB B level, parts per billion level. So that is why it was an accident. So you have to know about the chemicals and perspectives of the pre-design, design approaches to safety. Okay. So this is all about the basic overview of a chemical industry given in the first introduction chapter. I hope you remember the question answer we have discussed. So I hope you have remembered the question answer we have discussed. Excuse me. So if I'm going to repeat it again. So what comes under mesoscale process design? It is the particles and reactor selections. Both of the answers are right. Okay. So what is the time scale of molecular vibration? So it is 10 to the power -9 to 10 to the power -6 second. You please go through the lectures which is available in the YouTube link. So you will get all the information there, but still I am repeating it for the convenience. Then what is the length of the scale plant? It is 10 cube meter. Okay, that is 1 kilometer. Then fossil fuel formation is a slow reaction. It is true. Then what is the important property for process intensification? It is the rate of reaction is the important property for intensification. Next is what are the ways to intensify a process in an industry? It is all of the above actually. So if you mark one, then you will get the partial mark, but if you mark all of the above, you will get the full marks. Next, heat exchangers allow for a low heat transfer rates on a volume basis. It is false, right? Next, monolithic reactors are based on ceramic materials. It is true. Then comes, how does a single piece of monolith make a catalyst working? So this is the answer of how a catalyst works in a monolith reactor. Then the length scale of microreactor is around millimeter. This is true. Then what are the advantages of microreactor? You have studied all these things. So water must be removed from benzene prior to conversion to ethyl benzene by distillation. This is the safety. So this is a desulfurization. The steam gas is a mixture of CO plus H2. So these are the question: how can syngas form from natural gas? So this is by steam reforming. Then these are the questions you can get already in the YouTube link. So go through it. Separation is easy in case of heterogeneous catalysts, right? So pentane and hexane are used to make isoparaffins. This is true. So these are the questions related to the DMT and TPA plus ethylene glycol produce PET, that is polyethylene terephthalate. By combusting biomass, terpenes can be produced. This is false. Okay. So if you do pyrolysis on biomass, it will lead to the formation of liquid fuel. HMF is a biofuel. It's not. Okay. So PEF is found reacting which of the following chemicals? It is the FDCA and furan dicarboxylic acid, which last chapters has talked about, and ethylene glycol. The BTXT stands for toluene, right? Next, which of the following is not an organic raw material? That is oil. Oil is not an organic, it is inorganic. So aliphatic to aromatic conversion is known as catalytic reforming. So this is the epoxy ring of the ethene hexane. So I'm telling you repeatedly, go through the lectures, go through the lecture slides, go through the assignments, what is given to you every week, and go through the live sessions, questions also, because question will come from there only. Okay, if you go through the lectures with proper clarity, then you will be able to answer every question. Okay. So these are the questions for this is the structure of the inter and intermolecular hydrogen bonds present in cellulose. Then the hemicellulose structure, this is the galactose. Okay, so high pressure stream, medium pressure stream. What are the base chemicals is benzene, toluene, okay, xylene. These are all the base chemical, BTX. So naphtha gas oil produces pi gas by stream cracking. Okay, so which method? Remember the differentiation between the three methods. What is catalytic cracking? What is steam reforming? What is naphtha cracking? Okay, what is steam cracking? Steam cracking and steam reforming are two different things. Okay, remember that. Polar biomass produces syngas following which of the method? This is gasification method. Okay, so these are the these are the revision for the first week question. Next comes in the second week. We have learned about the acid reactions, sulfuric acid reactions, and thermodynamics. So first, it talked about the inorganic chemical industry. So it includes sulfur, nitrogen, phosphorus, and alkali. Right? Next, Next comes the uses of the inorganic chemicals. So sulfuric acid used in fertilizer, copper leaching, alkylation, refining, ammonia and nitric acid used in fertilizer, cyclohexane, nitrobenzene, chlorine used for polymer production, HCl production, NaOH for disinfectants. Okay, these are the uses. This is the production of inorganic chemicals globally, the statistics. Then the sulfuric acid development process. So very carefully go through the reactions are happening in the chamber or reactor. Okay, questions may come from the, like they might ask what is the product, what are the reactants. So it will be confusing after so many lectures you have studied. So please go through it separately and try to remember it. Then the old method and modern method of sulfuric acid production is the homogeneous catalyst, nitrogen oxides, and in modern method, heterogeneous catalyst, that is platinum and vanadium oxides are used. This is the sulfuric source of sulfur from oil refinery. Okay, so this is the how sulfur is acquired from oil refining. This is the process of that. Go through the flow chart also very carefully, because from the flow chart question will definitely come. Okay. So this is the sulfur dioxide reaction. The sulfur reacts with oxygen, produces sulfur dioxide. Then the catalytic oxidation of sulfur dioxide happens in presence of V2O5 vanadium pentoxide. It produces sulfur trioxide, and that sulfur trioxide is absorbed in water and produces sulfuric acid. Okay. So this is a conversion reactor and sulfuric acid production process. This is the sulfur burner. Okay. Dried and atomized molten sulfur are introduced together at one end of the sulfur burner. This talks about the how sulfur is calculated and how sulfur is burned to produce sulfur dioxide. Right? So this is the conversion reactor. So here platinum oxide is vanadium oxide is used in the because as a catalyst, because it is cheaper, good stability to poisons, and can be used with the porous inorganic support like silica or alumina. So this is the reactor used. So this has 4 beds because of its thermodynamics. We will be coming to it later. So this is the reaction. Next, why the effect of intermediate cooling and multiple catalytic beds. So intermediate cooling is required because sulfur dioxide is an exothermic reaction. So if the forward phase reactions happens, it will lead to huge amount of heat that will not suitable for the catalyst, and that will not suitable for the reaction to happen in environment also. So we need to control the temperature. So how will we control? So we are sending cooler or cooling material between the reactors. And also initially in the first bit you can see that only 65% conversion is there. So we need to make more pure sulfuric acid, right? So for that it is divided in the 4th bed, and where temperature is also controlled by sending the cooling material, and also the conversion is increased. That is why this four type of bed or 4 bed in an adiabatic reactor is required. That will control the temperature also, and that will facilitate the forward reaction also, and that will lead to the more production of sulfuric acid and with a very good quality. So this is what talked about it, effect of intermediate removal of sulfur trioxide. So if we remove the sulfur trioxide in between second bed and third bed, that will lead to more pure sulfuric, because in the last slide we have seen it is producing 98%. Now it is producing 99.7% pure sulfuric acid. Okay, so this is the structure of the Sulfuric acid production. So main is the sulfur burner where it produces sulfur dioxide. Then catalytic reactor it changes from sulfur dioxide to trioxide. Then absorption tower it is concentrated into sulfuric acid. This is the structure of the sulfuric acid production or flow sheet of the sulfuric acid production. You can notice the temperature changes from bed to bed. Right, I think this is clear. Next comes this is explaining the catalytic deactivation reaction, what is happening in the first bed reactor, first bed catalyst, its longevity and all that stuff. So this is about the sulfuric acid. Next is the inorganic chemical. It is for the Claus process, sulfur production of the Claus process. Okay, so here the source of hydrogen sulfide. So sulfur is also collected from hydrogen sulfide. So it is showing the source of the hydrogen sulfide itself. Then from many places we have seen the acid gas from different plants, other sulfur containing feed rocks rich in H2A, that is sour natural gas, off gas from hydro treating units, coal gasification plants from where we can calculate the sulfur. Next is the Claus process of the sulfur production. The Claus process is related to the sulfur production. Okay, so acid gas is coming here in the reactor or absorber, then it goes into the regenerator stream where catalyst is regenerated, and it is going to the separator where sulfur is recovered from gas phase or separating the gas phase. This is the Claus process equation. H2S plus oxidize produces sulfur. So this is the details of the Claus process. Then these are all the Claus catalysts we are using, the alkane or alkaline oxide. So it is detailing the Claus process for the sulfur production. This is also a Claus process, another way to produce liquid sulfur. These are the explanation or highlights, and you should definitely go through it to know what is the Claus process, and because question obviously will come from there. Yeah, this is the Scott process. Scott process is the shell Claus of gas treating process. This is another type of Claus process using in the shell industry. Okay, so this is the how liquid sulfur is recovered from the Scott process. These are described here. So I'm not going through all the questions from the material because already we have discussed and it is available in the YouTube. So just to show you. So these are the questions we have discussed. So this is the basic material for nylon 6. It is a not nitrobenzene. It is cyclohexanol. Okay. So these are the questions. This is the redetermining step for the lead chamber process. This is the sulfuric acid production, the equations involved in the sulfuric acid. From H2S we have studied, from pyrite ore we have studied how sulfur is collected and converted to sulfuric acid. Okay, so this is the thiophene from H2S production from thiophene. Okay, so sulfur burner, dried air and atomized molten sulfur is used. Then this is the sulfur trioxide conversion reactions. Okay, so this is the demister. Okay. Okay, I am going a little fast because I have to cover all the 12 lectures, 12 weeks lectures. So we have already discussed it separately in every week. So I think it is not impossible to understand if I go fast, right? Okay. So the third week we have learned about the I think in third week we have learned about the syngas. Yes, this is the syngas production. Syngas is a very, very important production. So syngas is a mixture of hydrogen and carbon monoxide. So the raw material is collected from natural gas to coal, and even biomass is another raw material for syngas production. So this is all about syngas. This is how this stream reforming happens. Catalytic reforming also. So autothermal reforming, the concept of autothermal reforming refers to a process that couples endothermic and exothermic reactions such as steam reforming and partial oxidation. So in the endothermic reactions, heat is required from outside, right? So we are producing heat from endothermic reaction first, and then we are using that heat into the endothermic reaction, and that will lead to the autothermal reforming. That will also generate less pollution, and as we are reusing the heat itself in the reaction, so it will reduce the cost of the plant also. So these are the syngas uses. What can be done with the syngas? This is a huge application of syngas. This is the flow schemes of syngas. So how syngas is produced from natural gas? This is the desulfurization happens, and then steam reforming it produces syngas from natural gas. Some heavy liquid or hydrocarbons also syngas can have produced. So first we need to do partial oxidation, then the soot removal. Soot removal means the contaminants, all the contaminants including the sulfur and some other things are removed here. Then sulfur removal, then syngas is produced. Then from coal, gasification occurs, particulate removal, sulfur removal, and syngas is produced. Okay. This is the flow schemes is detailed written here. How syngas is produced, you can see that this is the methanol or steam reforming or coal you can say or hydrocarbon you can say. So it is steam reformed with water and produces syngas. Carbon monoxide can also produce syngas. Okay, so from these are the partial reactions involved while producing syngas. That is the methane decomposition and water acid reactions, etc. This is the partial oxidation of methane to carbon monoxide and hydrogen production. Okay, so this is the stoichiometric composition of methane and steam. This is the temperature versus composition curve. Then this also all are these things. This is the process. This is the flow chart of steam reforming process. Go through the flow chart very well. Okay, very carefully. So in steam reforming, at very high temperature is made, that is 1000 Kelvin, more than 1000 Kelvin. Okay, carbon also is formed in the reaction as a side reaction. The methane slip also happen. Okay, this is the autothermal reforming. The heat is produced in the reactor by the burning of a portion of the feed with oxygen. So this ratio changes in the product distribution. In the presence of a catalyst, autothermal reforming is the combination of steam reforming and the partial oxidation. So for partial oxidation, we need heat from the outside, and steam reforming, it is producing heat. So I said opposite, sorry. So in the combustion, when partial oxidation happens and it produces in, and that heat is required in the reforming zone to proceed the reaction further. Okay. So this is the syngas production. Next, comes the cold gasification. Okay, so from cold gasification also I have said that syngas can be produced. So this is the cold gasification process. 32% raw material comes from the chemical industry. These are the heterogeneous gasification reaction occurs and as well as the homogeneous reaction occurs. So C coal is a carbon. Carbon is steam reformed to produce syngas. Then carbon reacts with carbon dioxide produces carbon monoxide. Okay, it also can react with hydrogen to produce methane. This is the water gas shift reaction. Okay, so this is the description for the coal gasification process. This is how a pyrolysis network happens in the coal from coal. So that is how it is written. Next is the thermodynamics. Okay, thermodynamics, like it is a equilibrium composition resulting from gasification of coal in an equimolar amount of steam as a function of temperature and pressure. So we will take about the how fast a reaction will occur. That talks about the kinetics and what is happening, what will be produced. Talks about the thermodynamics. Okay. So here is the composition. So you can see that forward reaction, the conversion is composition is 0.6% at the low pressure. The conversion happens more. So this is the allothermal process. These are the key processes. So what is said that for endothermic H2O gasification reaction, the CO and H2 mole percentages increases as the temperature rises. H2O drops as temperature increases. Okay. As a result of the exothermicity of the formation and the endothermicity of their conversion, both CO2 and CH4 experience a maximum. Due to the increased quality or quantity of molecules, a low pressure is beneficial for CO and H2 producing processes. As pressure increases, the CO2 and CH4 maxima migrate to higher temperatures. Okay. So this is for the autothermal case. Here also the key point is the properties of CO and CO2 are significantly greater than those of H2 and CH4, primarily due to the higher oxygen content of the fluid, especially at higher temperature. So allothermal process produces hydrogen-rich syngas, but autothermal process produces carbon monoxide-rich syngas. Okay, this is the reaction enthalpies. And that's it. In lecture 9, I talked about the gold gasifier. So this is the two process, Lurgi process or Lurgi Sasol Lurgi moving bed gasifier. So this is the moving bed gasifier. So what type of reactor they are using in the gasification process? This contains the this thing there, what is the temperature is going to be, where is the combustion zone, the reactor's base. Okay, what is happening inside the reactor and how a reactor should be chosen in the gasification process, this is talked about here. So they also have the disadvantages and advantages. Okay. So if this is last time we have this time here it is the moving bed gasifier, but here it is the fluidized bed gasifier. Okay, so there are different type of reactor or gasifier is used to check which one is the suitable or which one is the best for a certain coal. So this is the fluidized gasifier. This is the fluidized bed gasifier is continuing here also. Next comes the entrant flow gasifier. Okay, this is the third type of entrant flow gasifier. So this is the type of reactor. Okay, so syngas is collected on the top. So previously in the moving bed gasifier, syngas is collected from the bottom. Okay, so comparison if you see, so due to its counter current manner operation, the moving bed gas reactor achieves the lowest exit gas temperature. The coal gas efficiency represents the chemical energy in the syngas relative to the chemical energy in the entering coal is a critical indicator of the efficiency of coal gasification determined by the heating values or standard temperature. This is condensate. Okay. Here some comparisons are given. So if you see this one, so comparison is that non-coking coal is used in moving bed. This is a reactive coal. This is all type of coal can be used in the entrant flow. Coal size should be 3 to 50 millimeter. This should be less than 5 millimeter. This is less than 0.1. So entrant flow uses very smaller size of coal particle. Then temperature is maintained high in the entrant flow. Outlet temperature is also high in the entrant flow. Carbon conversion is high in the moving bed as well as in the entrant flow bed. Okay. So these are the advantages of using entrant flow. So this is the comparison. You can see that they are, if each one is favorable in certain conditions. So depending on the coal size or coal type, we have to choose the gasifier. Okay. So here the comparison is talked about details. So what kind of gases are produced at the end? Okay, so in the entrant flow, you can see only the HO and CO produced. Okay, only the HO and CO produced, nothing else is produced. But here the CO concentration is high. But in case of moving bed flow, you can see that all type of gases are produced, but it produces hydrogen rich syngas. Okay, but along with that H2O, CO2, CH4, COS, H2S, HCN, NH3 mixture, all are acid gases, all are produced. So it will be difficult for moving bed gasifier product to separate the syngas, right? But it is easier for entrant flow. But it produces CO rich syngas. So depending on the requirement, we will use the gasifiers. So this is the acidification technology applications they have talked about. So what type of gasifier used in different industries? Shell entrant gasifier. Then comes the GE entrant gasifier. Then COP entrant gasifier. All of them has different kind of reactor or some sort of changes in each of them. Mainly the reactant and product is obviously the same, but they are changing depending on the efficiency. Okay, so these are the applications. So you can see that how many processes syngas can be used. Okay, from alkene production, crude iron production, hydrotreating, electricity, heavy ash production, everything. Okay. So from coal gas or syngas, this methane also be produced. Methane can also be produced. This is the integrated gasification cycle. Hmm. So this also has advantages and disadvantages. Okay, this is a polygeneration in IGCC power plant with carbon capture. It is acid gas removal step, and the third week is done for the coal gasification and syngas production. So here you can see the sources of syngas production, everything, coal gas, naphtha, heavier hydrocarbon, everything. So here ophthalmol reaction, it refers to a process that couples enthermic and exothermic reactions such as steam reforming and partial oxidation. So partial oxidation is exothermic, steam reforming is endothermic. Okay, so this is the syngas production reactions we have just seen. This is the coal gasification reactions we have discussed. Here also, you please go through the live sessions videos in YouTube. You will get all the answers there. So these flow charts are very important and reactions are also important. Okay. I hope you are understanding what I am saying. So now we proceed to the next lecture, that is week 4. In the week 4, the mainly discussion is about the thermodynamics and nitrogen. Here the nitrogen is focused as an inorganic chemical. So nitrogen means production of ammonia, nitric acid, etc. So this is the background of ammonia. Ammonia, from where ammonia is coming. Okay. So limestone, it produces CaC2 plus carbon monoxide. Then it reacts with N2. It produces CaCN2, and then CaCN2 reacts with water, produces CaCO3, calcium carbonate, and our desired ammonia. There are multiple processes to produce ammonia. Will be knowing that. So there are very much products. Why ammonia is called as base chemical? You can understand from here, because ammonia has multiple applications. Okay, so this is the thermodynamics of the ammonia production. Also, nitrogen and hydrogen can produce ammonia. You know that. So these are the different types of reactors used in ammonia production. The first one is the ICI quench reactor. Okay, so here quench fluid is given, and that is how it is maintained the temperature, because this is an exam, otherwise it is an examic process. Right? So this is the ICI quench reactor. Next comes the Kellogg's quench reactor. Okay, how the reduction of the flow and reduction of using quench is differed from the ICI quench reactor. Next is the Kellogg's quench reactors horizontal one. Okay, so it has large catalytic area per unit volume, lower presence pressure drop, smaller catalyst. So it has some advantages compared to the previous ones. This is a Haldor-Topsøe reactor. Here it is a radial flow reactor. Two annular catalyst beds are used through which, for gas flow in the reduction reaction, heat exchanger located at the bottom helps with upward flow of feed gas through the central pipe towards the catalyst. Okay. This is the 4 different type of reactor. Next comes the multi-bed converter with direct indirect cooling. Then comes the highlights, so thermodynamics main. Okay. So next, this is a plant, integrated ammonia plant, hydrogen recovery. This is ammonia synthesis loop. Plus seeing that in the reactor, feed gas is going along with the N2 and H2, and the separators. In the separators, gas is purged and liquid ammonia is collected from the bottom. Okay, this is ammonia synthesis loop. This is a two-stage product, because this is a two-stage product. So from two-stage, to avoid the compression of liquid ammonia, here two-stage separator product separator is used. This is the overall process of ammonia production and recovery. Desulfurization, reforming, water gas shift reaction, CO2 removal, methanation, condensation, and ammonia synthesis. Okay. Now this is the primary removing, reforming, and sulfur removal. So how sulfur is removed from the ammonia, liquid ammonia. This is the secondary reforming and the CO2 removal process from the ammonia synthesis. Okay. This is the water gas reaction happens in the ammonia synthesis process due to the presence of carbon monoxide and sulfur, carbon dioxide, etc. Okay, these are the secondary reforming chart. Lecture 13. It is talk about also the continuation of the previous one. So how the Pars gases or purification happens for ammonia, it happens by cryogenic distillation, absorption, adsorption, and membrane separation process. This is how the hydrogen is recovered with TCA temperature swing absorption by rising the temperature and the pressure swing absorption by reducing the pressure. Okay. So this is how hydrogen is recovered from PSA or TSA state after producing ammonia. 4 reactor beds are used. There are 4 absorbers actually. In the first absorber, pressure is high. The second absorber pressure little bit in the step 2 pressure is reduced. In the regeneration the pressure is very small, and in the fourth step pressure is again increased for the first absorber. In the second absorber, in step 1 pressure is increasing. It is maximum in the step 2, and it is lower in the regeneration happens in the last step. In the third absorber, regeneration happens in the first step itself, so the pressure is very low. In the fourth step, pressure regeneration happens in the step 2. Okay. This is the hydrogen recovery process through pressure reduction or repressurization. Okay, this is a membrane separation process. How hydrogen can also be separated by membrane separation process. This is there. Okay. So this is the hydrogen recovery is done from the ammonia. So now the urea production. So urea is also an important fertilizer used from ammonia, produced from ammonia. So how urea is used? We'll be seeing it is a urea is a non-toxic compound. So how urea is used? Ammonia reacts with carbon dioxide, produces ammonium carbamate. Okay, and this ammonia carbamate decomposed slow reaction. This is slow reaction decomposed to produce urea plus water. The temperature, reactor temperature is maintained at 450 to 480 Kelvin. Okay, so the main reactant is the ammonia and carbon dioxide. It produces ammonium carbamate, then from it decomposes into producing urea. So this is the once through urea processes. Okay, this is the urea reactor where the reaction happens. This is the carbamate decomposer. Here the ammonium carbamate is produced. Here the carbamate decomposes. Here carbamate decomposes and produces urea, and all the other gases and urea solution is separated in the distillation column. Okay, then stripping process for urea, how urea is separated. This is talk about that. So how urea is stripped. So based on the CO2 stripping process, it is shown here. Then what type of heat exchanger is used? That is a shell, falling film type shell and heat exchanger is used in the stripping process. This is another cool reactor used to separate or to strip CO2 that is shown. Okay, so go through the lectures. You will understand how to handle the corrosion. This is the finishing process of the urea solution. Okay, urea. So now urea is collected after the stripping and it is now separated in the urea solution. It goes into this. This is the vacuum evaporator. 99% of molten urea is collected. It passes through the reactor where cooling air is separated and urea granule is collected. Okay. So last lecture is about nitric acid production. So we have learned the ammonia production, then the urea production. Last comes the nitric acid production. Okay. So catalytic oxidation of ammonia in presence of water, that is the Ostwald process, is the modern process to produce nitric acid. You can see here, in presence of oxygen, ammonia produces nitric acid. And these are the other processes involved, the site reaction involved in the production of nitric acid. Here, it also produces nitrous oxide, nitrogen dioxide, etc. Okay. So, oxidation, two methods nitric acid can be produced. Oxidation, condensation, and absorption are used in the first procedure to make a weak nitric acid. Nitric acid may be made from a weak nitric acid by combining dehydration, bleaching, condensing, and absorption in the second. So, it will lead to the 90% nitric acid. Okay. Ammonia oxidation happens, then nitric oxide, it produces nitric oxide, then nitric oxide oxidation produces the nitrogen dioxide and it produces weak nitric acid. Okay, so these steps here, these steps are talked about separately. It is producing weak nitric acid, right? This is a flow chart, single pressure nitric acid process. This is the dual pressure nitric acid process. This is the important part of the nitric acid production is the compression or expansion part. So this need to be careful here. High level compressor is used, medium level compressor is used, and then the expander is also used. Okay. Selective catalytic reaction, non-selective catalytic reaction is used. Reduction is used to produce nitric acid. Okay. So so in the second most manufactured chemical is ammonia. Okay, so natural fertilizer. Then comes the ammonia reacting ethanol produces methylamines. Then the Kellogg reactor is used in direct cooling method. Okay, two stages used to avoid the compression of liquid ammonia. Then how does an integrated ammonia plant work? So this is the flow chart for ammonia production. Then comes the hydrogen recovery process with TCA and PCA. Okay, so this is all about the nitrogen production, ammonia production, and urea production. So in week 5, in week 5, phosphoric acid production is discussed in the dihydrate process. There are many other ways also are there also to produce the phosphoric acid. So first one is the dihydrate process. So how phosphoric acid is produced? So we'll see here. So you can see that calcium phosphate, tricalcium phosphate is converted into phosphoric acid in the presence of sulfuric acid, and it also produces gypsum. Gypsum is the calcium sulfate, CaSO4, right? So phosphate rock and sulfuric acid react in a self-contained manner and also produces H3PO4 and CaSO4. Okay. So this is the equilibrium temperature. This is the operating conditions of the dihydrate process. The different processes are used to produce phosphoric acid. First one is the dihydrate process, which we are talking here in this PDF. Then the hemihydrate process. There are two types of hemihydrate process. There is the hemidihydrate single stage process, hemidihydrate double stage process. Then dihemihydrate process. Then hemihydrate recrystallization process. Okay. So what are the differences? So in the dihydrate process, gypsum is precipitated as dihydrate. Okay, CaSO4.2H2. In hemihydrate process, calcium sulfate or gypsum is first precipitated at hemihydrate and the phosphoric acid is separated. Hemihydrate is recrystallized with more water as dihydrate. In the dihydrate hemihydrate process, acylation is conducted under dihydrate condition. Calcium sulfate is recrystallized to hemihydrate. And in the hemihydrate crystallization process, the hemihydrate recrystallizes to dihydrate even before separating the hemihydrate. So filtration steps. So here it produces directly the dihydrate and not the hemihydrate first. Okay, so it produces the step. So these steps are discussed here in detail. This is a dihydrate process. Okay, this is a process flow sheet: grinding, reaction, filtration, and concentration. Here, the next process are come. This is the hemihydrate process. So we have learned the dihydrate. So here the hemihydrate process is talked about. Okay. So here grinding is not necessary, but in a dihydrate process, grinding of the uh, phosphate rock was necessary. This is a recrystallization process, hemihydrate recrystallization process, hemidihydrate process, and dihydrate hemihydrate process. So here the three basic routes we have talked about. So acid addition under hemihydrate production condition. In the HRC process, so recrystallize to dehydrate without intermediate hemihydrate separation. Okay. Here in the HDH process, product is separated and recrystallization takes place from hemihydrate to dihydrate. And in the DHHA process, separate product recrystallizes the hemihydrate, filter the return liquor to process. Okay. So this is the HRC process. Multi-reactor dihydrate procedure. It is used. So here efficiency is 97%. Next is the HDH process, hemidihydrate process. Here the efficiency produces purer acid from the previous one. Go through the disadvantages and advantages to understand the difference between the processes. Here the DHHH process, where the most high efficiency of P2O5 or 98% is acquired. This is the advantage, but there are also the disadvantages also are there. Okay. Last, the repulping process. Advantage is pure gypsum is got and high efficiency, but disadvantage is the high capital cost. Right? Next is the emission abatement in phosphoric acid plants. So how emission is stopped from the phosphoric acid plants? Otherwise, it will lead to pollution, right? So this is the theory basically. Hmm. So fluorine is recovered so that it doesn't mm, emit into the environment. This is a gypsum disposal process. Okay. This is the raw material storage process. This is the environmental data. So input requirement and output production of the phosphoric acid reaction emissions into the air. So what is emitted? 10 to 15% of the fluorine content in the phosphate rock is released during the acidulation and filtration stage. Okay, so that is why we need the emissions abatement. So this is all about that: dust emissions, fluid emissions, contamination of water, radionuclides. This is a summary of the bad emission, and that's it. So this is the chlorine production process. Okay. This is the physical properties of chlorine. So this is the physical properties of chlorine. Then comes the introductions that from where chlorine can be found in large quantity of rock soils. These are the sources of chlorine: sodium chloride, potassium chloride, uh, bisulfite, carnallite, kyanite, everything. Then how chlorine was produced initially from MnO2. Then the chloralkali process. The chloralkali process, NaCl or KCl reacted with water produces chlorine and NaOH. Okay, so this is the cell where chlorine is generated. Next comes the mercury cell process. So three types, in three ways chlorine can be produced. First one is the mercury cell process. Okay, so you'll see the here in the anode area Cl2 is produced, and in the cathode area NaHg produced, then it produces in concentrated NaOH. Okay, and Cl2 is already separate. So this is the flow sheet of the Mercalli process. Then is a diaphragm cell. Diaphragm same in analyte is given. So microporous diaphragm separated the anode and the cathode. Here in the anode Cl2 is generated, in the cathode H2 is generated. This is a flow diagram of the diaphragm process of chlorine production. Okay. This is the membrane cell process. Third one is the membrane cell process. In the membrane cell process, also Cl2 generated in the here, and along with that NaOH is also produced in the, along with the hydrogen, NaOH also produced in this cathode zone. Okay. This is a flow diagram of the membrane cell process. You learn that things carefully, so you'll be you can understand the differences. And the last lecture of week 5 is the soda ash production. Okay, so soda ash is used in glass making industries, making soaps, detergents, water treatment, paper making, and removal of SO2 from flue gases in power station. Okay, these are the properties of soda ash. So this is a Liebang process from where soda ash is produced. Hmm. This is the Stona process. This is a soda ash is a sodium carbonate, right? So this is the monohydrate process from used for Trona ore, crushing, then calcination, then dissolution with water, then clarification happens, filtration, carbon treatment, evaporation, crystallization, centrifugation. This crystal is recycled back to the evaporation section, then drying, shipping, and sodium carbonate is generated. This is a sesqui carbonate process for sodium carbonate production. This is the Solvay process. Solvay process is one of the most important process used in the industry to produce soda ash. Here, salt and limestones are used as raw material. Okay, this procedure employs sodium chloride to give sodium ions. Sodium ions and calcium carbonate to provide carbonate ions for the sodium carbonate. The different products are formed. Light ash, that is the light sodium carbonate, granular sodium carbonate is the heavy ash, and the refined sodium hydrogen carbonate. Okay, so these are the reactions involved in the Solvay process, which are very important. Okay, this is all. These are also the reactions. This is the process in detail. This is the flow diagram of the Solvay process. Okay, these are the products we have seen. Okay, the advantages of and disadvantages of the Solvay process. Right. So here So here all about phosphorus and soda ash and chlorine. Okay, the dihydrogen phosphate. So this is the reactions involved in the phosphoric acid production through dihydrate process. Okay, so this is the gypsum and dihydrate and hemihydrate process. Then comes the phosphoric chlorine does to phosphoric acid. So CF2 is present in the reaction, so it reacts with hydrogen, produces hydrogen fluoride and Ca2 plus. This hydrogen fluoride reacts with silicon. silicon oxide SiO2 and produces SiF4. SiF4 reacts with water and produces fluorosilicic acid. Okay, hexafluorosilicic acid, which is not good for the environment. Okay. What is used to precipitate fluorine as solid calcium fluoride? That is limestone. Then these are the fetching water. Yes. Then sources of radionuclide exposure: the direct irradiation from gamma radiation, and airborne emission of radon and dust. The phosphoric acid is explosive or not. Weldon method is used to bleach chlorine, to use chlorine as bleaching material. Okay, so these are the different sources of chlorine. These are the catalytic method of producing chlorine, and this is the alkali method of producing chlorine. Okay, then Leblanc process of soda ash production. We have just seen. Then byproduct of solid process is the CaCl2 plus H2. Okay, so week 5 is all about this. Next is the week 6. So in the week 6, we talked about the sir has taught about the heterogeneous catalyst design and reactor types. Heterogeneous catalysts tend to be smaller in scale, is the homogeneous catalysts are tend to be smaller scale and more targeted. Heterogeneous catalysts in continuous processes are often preferred in industrial catalysis from an engineering standpoint. Okay, because catalyst separation is easier with heterogeneous catalyst compared to the homogeneous one. Regeneration is more flexible and cost is less expensive. Okay, so this is the catalytic design, how catalyst is designed, how a heterogeneous catalyst is designed. This is the rate of the reaction of the heterogeneous catalyst. Okay. Thiel modulus is defined here for calculating the rate of reaction for a heterogeneous catalyst. This the design continues. Then the different shapes of heterogeneous catalyst: the sphere shape, pellet shape, cylindrical extruded, tri-lobe, then hollow extruded, ring, wagon wheel, and the monolith. So different type of react for designing heterogeneous catalyst, different type of reactor required. So the number and kind of phases is need to be known. Then the mixing and contact patterns need to be known, whether it is co-current, counter-current, or cross-current. The reaction kinetics, residue reaction enthalpies, deactivation of the catalyst, everything is to be known to run a reactor, heterogeneous catalyst in a reactor. Okay, so these are the solid catalyst gas phase reaction happens in the fixed bed reactor. So this is the simple fixed bed reactor. You can see this is the if we are with the combustion zone. This is the combustion zone because this is the burner here. This is a radial flow, so it comes with radially. This is a monolith reactor. Okay. Then reactors with moving catalyst. So in the previous slide, we have seen the stationary catalyst. So here the moving catalyst. Okay. A moving bed reactor where the catalyst is moving continuously with the reactor. This is a fluidized bed reactor where the fluid is feed is sent, and inside there is the dense phase with the catalyst is there. And it produces gas bubble with the mixing and all. This is the entrance flow reactor. Okay. So this is the reactors for solid catalyzed gas liquid reaction. So you can see that gas liquid reactor, solid catalyzed gas liquid reactors, triple bed reactors, monolith reactors, This is the solid catalyst, then three-phase fluidized bed reactor and mechanical star tank reactor. This is a gas phase reaction. So what type of heterogeneous catalysts are used in the different reactor and what are the applications? So these are, you can see naphtha production, catalytic reforming, steam reforming, water gas reaction, methanation, ammonia synthesis and methanol synthesis. Okay. So monolith reactor, exhaust gas cleaning. For exhaust gas cleaning, monolith reactors are used, radial flow, catalytic cleaning, autothermic reforming, fixed bed with combustion zone, then moving bed. Reactor application is catalytic reforming, fluidized bed is classical FCC, and entrant flow reactor is modern FCC process. Okay. And gas liquid phase reaction, particle bed, the heavy oil fractions, moving bed, hydrogenation of residue, and three-phase fluidized bed is hydrogenation of residues. So these are the reactor types, different types of discuss in details. Fluidized bed, fixed bed. Okay, this is the heat exchanger used in this type of beds. Then there comes the moving beds, catalytic deactivation. Okay, how catalysts are deactivated in this type of beds is discussed here. Then safety and scale up. For safety and scale up, what type of industry and what type of catalyst, heterogeneous catalyst is required is talked about here. This is the zeolites and production of isobutane. This is also about the catalyst only. So this is the structure of the zeolite. Okay. What type of zeolites are used here? The reactant zeolite depends on the reactant selectivity, transition state selectivity, and product selectivity. Okay. Okay. Different type of zeolites are talked about here. This is the isobutene, where zeolite is used. Production of isobutene. So simplified flow sheet of N-butene isomerization, you can see that here the ferrite solid catalyst, that is the heterogeneous catalyst, is used in the reactor for the production of butene. Okay. So how now comes the production of ethyl benzene. So benzene reacts with ethene, produces ethyl benzene. Okay. So ethyl benzene can convert to diethyl benzene after reacting with benzene, and it leads to the polybenzene, or trans as alkylation also happen. So we need to stop the formation of polyethyl benzene. Okay. Otherwise, there is no point of the reaction. So this is the ethyl benzene production. Mole versus thermodynamic curve. The process development of ethyl benzene. This is the catalyst development. So commercially viable method is vapor phase method utilizing a ZSM fine catalyst, and Mobil introduced MCM22 zeolite based catalyst. Okay. This is the Monsanto-Lomas process for ethyl benzene production. Then comes this is a Monsanto-Lomas process, one of the process. So corrosion can happen here. Production of polluting waste. These are the disadvantages of the Monsanto process. Okay. Another process is the Mobil-Badger process. This is the gas phase. Monsanto-Lomas process is a liquid phase reaction, but Mobil-Badger process is the gas phase reaction. Okay. Yes, LSM5 zeolite is used in the gas phase alkylation procedure. The gas phase mobile Bézier process of ethyl benzene production. We go through the uh, flow chart very carefully and understand the difference between two of the processes. So here you can see that it is very difficult to separate. It is false because they are very easy to separate. Reaction kinetics and diffusion rates of the reactors and products. Then comes the solute because to lose the pressure drop in fixed bed reactor, we need to make the catalyst particle very smaller. That will lead to the smaller. That will lead to the increasing tiny particles are needed to lose pressure drop. No, large particles are needed because large particle means low surface to volume ratio, and that will lead to low pressure drop. Okay? This is the internal effectiveness factor. Similarly, these concepts comes with the parameter of heterogeneous catalyst reactor. These are a defined type of bed where fixed bed is there. This is not this bed is not moving. In the fluidized bed moves, and entrant means it is overflowed from the bed. Okay. So this is a zeolite where Al3 plus and Si4 plus oxygen is there. Crystalline micropore structure. Reactants of MTB and ETB is the methanol and ethanol. Then all about relation to trans-alkylation process of benzene, ethyl benzene production. Then it is done. Next in week 7, what is taught? So it is a flow reversal and production of styrene. Okay. So exothermic reaction, then comes the different type of flow reversal reactor. So reactor with periodic flow reversal. So here feeding a hot catalyst bed with relatively cold gas will cool the entrance side of the bed, but the exit side of the bed will get hotter due to the heat of reaction. Okay, so what type of reactor should we use in an exothermic reaction? That is the first one is a reactor with periodic flow reversal. So this is explained here. Inlet gas is certain time later inlet gradient gets cooled and while the exit or outflow has heated. Right after a significant number of flow reversal oscillating or stationary state is obtained, and by reversing the flow at a certain time heat can be controlled in the reactor. So you can see that with this reactor with RPFR reactor with periodic flow reversal, you can control the temperature in an exothermic reaction, right? So this is the process, commercial applications of RPFR, then the exothermic reactions and production of styrene. Styrene produced from ethyl benzene converts to styrene and dehydrogenation happens and produces hydrogen, right? So ethyl benzene dehydrogenation. So production of styrene with the help of RPFR. Okay, atomic temperature drop at 100%, ethyl benzene conversion. Ethyl benzene and steam introduced in reactor. Additional steam is fed concurrently at one or more downstream locations. flow direction of the stream is periodically reversed between the reactor ends so the temperature can be maintained. Inert beds serve as the heat exchange medium, prevents the occurrence of the reverse reaction which otherwise would have taken place at the end of the cooler reactor if the catalyst material had been present, right? These are the advantages of using RPFR in the production of styrene. The redox OH process or DH process to produce styrene. Okay, so these are the things. So this is it. Yeah, 25th lecture. Selective oxidation process and ethene production. Okay, so selective oxidation. So for oxidation, ethylene oxide is needed to produce because its application is huge. Ethylene glycol is one of them, accounting for about 60% use. Otherwise, for surfactant, ethanol amines. Okay, so this is the ethene oxide plants. So you can see that ethene is partially oxidized to produce ethene oxide, right? Byproducts are simply carbon dioxide. So ethene oxide can also be reacted if these get oxidized and produces carbon dioxide and water. Okay, so these are the process flow sheet of the ethene oxide plants where inlet ethene one promoter is there, methane and accessory. There is a feed mixture of ethene, oxygen and inerts. And that has been preheated. Considerable excess of ethene is utilized to maintain low conversion and strong selectivity towards the ethene oxide. Gas leaving the reactor are cooled by heat exchanger. You can see here the heat exchanger with the feed gas and delivered to a column where water is used to absorb ethene oxide, which is only the present at a concentration of 1 to mole percent. Ethene oxide rich aqueous solution that exits the bottom of the ethene oxide absorber is passed through a stripping column, that is the U absorber, and ethene oxide is separated at the top. Okay. So that is how it goes in. Pressure has no effect on conversion at ordinary reaction temperature, but higher pressure helps in the absorption of ethene oxide by water. Now ethene oxide absorber receives the bottom stream comprising water and some ethene glycol is generated when ethene oxide reacts with water. Then these two columns of distillation separate ethene oxide from light ends and residual water. You can see here to prevent the accumulation of inerts, a small portion of gas exiting the top of the ethene oxide absorber is purged. After compression, a portion of the recycling gas is diverted to an absorber where carbon dioxide is absorbed before being recycled to the reactor. Then ethene and oxygen generate explosive combinations at certain amounts. Heat to the reactor has to be 20 to 40% ethene and around 7 mole percent oxygen. Then it will cross the flammability limit, upper flammability limit. Okay, so this is here. Here oxygen is used, so comparison is happening here. If we use oxygen, so ethene is required 15 to 40%. If air is then it is required 20 to 10%. And conversion will happen 7 to 15% in the oxygen base, but in air base it will be to 20 to 65%. Okay, that is pretty huge. Okay, now this is the production of maleic anhydride. So from butane it produces butene, then dibutane, then furan, then maleic anhydride. Right? This is the production flow chart. Then the applications, advantages, disadvantages, and that's it. So this is a monolithic reactor for automotive emissions. Okay, so this is the monolith reactors, most providing a conceptually simply structured reactors, continuous constructions composed of tiny parallel channels, ceramic or metallic support, then channels, round channels, triangular, square, hexagonal, other shapes. An entire monolithic block can be modeled to fit into the reaction chamber. The monolith catalyst, this is the substrate, this is the wash coat, and this is the catalytic species. So this is all about the monolith reactors. Okay. So in this uh, session, we have discussed the RPFR, about the RPFR, okay, where the flow of the feed changes periodically. Mhm. Then the physical condition of catalyst bed is used in building component material, high heat capacity, and large particle diameter. Pressure drop of the bed is also reduced. In which of the following is so this is about the incidence of styrene, ABS plastic is produced, SBR plastic is produced. Write the synthesis equation of styrene. This is the styrene production reaction. Benzene to ethene produces ethyl benzene, and then it converts to styrene and H2. Okay, so this is the ethene oxide production. So, so how ethene oxide is produced from chlorine. This one is the direct ethene oxide production step by oxidation, right? So these are the equations we discussed, or these are the questions we discussed earlier also. Next, in the this is for the methanol production. Okay, so methanol is one of the most important base chemicals in the industry because its applications is huge. You cannot think of the applications. You can see the uses, right? It produces HCN, acetone, pisilene, PMMA, PTP, LDP, HDP, everything. Okay, so main reaction is from syngas. Only methanol can be produced. Water acid reaction is used as the coupling reaction. The reaction thermodynamics and catalysts use. Okay, so syngas for methanol production. So we talked about the syngas, then excess of hydrogen. What to do with the excess of hydrogen? Then the conventional process flow sheet for the ethanol production from syngas. So syngas goes into the activated carbon filter, then the reactor, Then it goes into the high pressure separator where H2 is purged, right? And the product goes to the low pressure separator and crude methanol is separated. This is a conventional process. And ICI low pressure in conventional process of methanol production, high pressure is used, but in the ICI process, low methanol pressure is used. Okay. Here, single catalyst base is utilized in an adiabatic reactor, adding cool reactant gas at varying heights when the catalyst base quenches the process. Okay. So this is the ICI low pressure method for methanol production. This is again the methanol production is due. This is a Lurgi process another. So here only the difference is the reactor from the ICI process. Here multitubular reactor is used, but in the ICI process, adiabatic reactor was used, right? This is the Lurgi process. In the Haldor-Topsøe process, succession of adiabatic reactors are used. Okay, this is the radial method, radial reactor. Okay, also slurry reactor also can be used. So these are the different type of reactors, so there are different types of methods where only the difference is the reactor to produce the methanol. Okay. Next, next comes the formaldehyde production. Okay, so from methanol only formaldehyde will be produced, right? So this is the formaldehyde production reaction. This is the flow sheet. And that's it. So in the Fischer-Tropsch synthesis is an important process for methanol production. So here the synthetic fuels are discussed. Okay. So primary routes from coal, biomass, and natural gas to liquid fuels via syngas production is here discussed here. Then this is the Fischer-Tropsch process. This is the Fischer-Tropsch process equation. Main reaction to produces alkanes, and side reaction is the water gastric reaction, alcohol production, Bordet reaction, etc. Then the thermodynamics of the Fischer-Tropsch process. Okay, this is the reactions in the Fischer-Tropsch process. Catalyst used in the Fischer-Tropsch process, iron-based catalysts. Then cobalt-based catalysts also can be used. So both of them have some advantages and disadvantages. So you have to change the using a catalyst based on the requirement. Then comes the deuterium-based catalyst. This is a summary of that one. So what is the summary? Ft synthesis catalyst now in use are the cobalt or iron-based. Cobalt catalysts have higher activity and higher chain growth probability, work better in the manufacturing of fuel and worksys. Okay, use of iron catalyst at higher temperatures is optimal for the synthesis of gasoline and linear alkyl. Additionally, the low H2CO ratio of coal-derived syngas makes iron catalyst the catalyst of choice. Okay, so these are the significance of FT process. So the reactors used in the FT process is the first one is the multitubular reactor. Then slurry reactor is used. So there are the 4 different types of reactors. You will see the difference if you go to the description. Then the fluidized bed reactor comes. Then the circulating fluidized bed reactor. Okay. So these are the difference and comparison of the reactors will be shown in the next. So here reactor height is 12 meter for multi-tubular, then slurry is 22, 46. So a circulating fluidized bed reactor has more height, then diameter is more for the fixed fluidized bed. The reactor capacity is more for the fixed fluidized bed as well. Okay. So this is the comparison of the four. So we'll be using any of the reactors depending upon our requirements. So this is the Sasol and SDMS process of the FT process is discussed here. So we'll not go through everything. So these are the huge flow sheets that there you can go through, or you can note down the important points what sir has talked about in the class. Okay. So this is the methanol reacts with syngas produces alcohol. Okay. Then these are all the reactions, methanol formation reactions, then the thermodynamic methanol details is given in the slides and you will get the videos in the YouTube. These are the FT processes. What can be produced from FT processes is shown there. Excuse me. Okay. So now proceeding to the week 9. So it is most often the methanol to gasoline, Haldor-Topsoe and T-gas process. So methanol to gasoline MTG process and the T-gas process. Okay. So methanol to gasoline process, methanol converts to DME, and DME produces alkenes, gasoline alkenes, then higher order alkenes, then from heavy order alkenes, and it produces heavy order alkenes. This is the gasoline, right? So this is the MTG process. So both way can use coal biomass, natural gas, syngas generation, syngas can do Fischer-Tropsch, refined and produces naphtha diesel, and CH3COH syngas can produce methanol, and then methanol to gasoline can be produced. This is the MTG process. Okay. The RSM5 is the catalyst. This is the flow chart of the MTG process. So low temperature FT process, it will produce waxes more, then high temperature FT process produces more amount of gasoline, but MTG process produces 89% of gasoline. Okay, so and only 10% of LPG, or 11% of 10% of LPG and 1% of fuel gas. Other things are not produced, so it will be easier in the MTG process to separate gasoline. Then comes the T-gas process. Okay. So it directly converts to gasoline, and ethanol and DME is not separated. DME is not separated in the T-gas process. Okay, this is the difference from the MTG. It is talks about the fuel additives. Hmm. We'll go through the lectures. We'll understand what are the fuel additives they have talked about, right? Then the last lecture of the week 9. It's more about the homogeneous catalyst, because why homogeneous catalyst is difficult to separate and how it can be separated. So these are discussed here. Hmm. So here you can see as the disadvantages of homogeneous catalyst is talked about. Okay, is a comparison of homogeneous catalysts, that in which processes homogeneous catalysts are used. That is the acetic acid production. In acetic acid production use oxo alcohols on alkenes, dimethyl tryptophan, terephthalic acid processes. Homogeneous catalysts are used, but methanol production, ammonia production, sulfuric acid production, and CCC, ethylene oxide production, heterogeneous catalysts are used. But you have to notice what are the chemical catalysts are used in the heterogeneous. So copper, iron-based, vanadium-based, zeolite-based, and silver-based are heterogeneous catalysts, whereas rhodium, iridium, cobalt-based, nickel-based, these are the homogeneous catalysts. Okay. So this is now comes the acetic acid production reaction from methanol or from butane. Then okay, so first one is the Monsanto process is from the butane oxidation, acetic acid produced. Then the carbonylation, methanol carbonylation, and it produces acetic acid, right? Then comes the Cativa process and all. Okay, so I'm not showing you the question answers already discussed previously in the previous sessions. So we'll notice from there. So here, this is the methanol carbonylation is talked about detail. So last we have seen the methanol carbonylation. So it is methanol carbonylation produces acetic acid. So this is talked about this in with the mechanism, reaction mechanism, the catalytic reaction mechanism, and the thermodynamics, all that stuff. And the catalyst, which catalyst is used, rhodium is used or iridium is used, and whose selectivity is higher is talked about here. Okay, this is a flow sheet. This is it. So this is the hydroformylation of the propene. Hydroformylation of propene produces butyldehyde on N-butyldehyde. This is for the separation of butyldehyde and butyldehyde and the subsequent or side reactions, oxo alcohols. Okay, this is it. Then here you can see the hydroformylation of higher alkene is discussed here. This is a biphysical system process. Then higher alkenes produces alcohol. Okay, hydroformylation of higher alkenes produces alcohol. Okay, so this is a cobalt-based process where cobalt is used as a catalyst. Okay, in the last lecture of week 10, this is the ethene oligomerization. So ethene oligomerization, you can see with the shock process. So different range of alkenes are produced here. Higher alkene, lower alkene, depending on our requirement. In week 11, dimethyl terephthalate and terephthalic acid production is there, right? So this is it. So how from the xylene toluic acid, methyl toluate, Wheaton process, then comes the Amoco process. DMT is produced from the Wheaton process, and from the Amoco process, TPA is used, right? So this is a Wheaton flow sheet. And this is the Amoco flow sheet. Next comes the biorefinery products. Okay, so biorefinery is used nowadays because fuel, you know that fuel gas is almost finished, so and it creates more pollution. So we are using bio-based product. We want to use bio-based product. That is why biorefinery is used, because bio-based products are renewable resources and plant material is used as the main ingredient, and they are biodegradable and they will sustainable. They are sustainable also. So this is the sustainable part of the lectures. So here the optimal synthesis of sustainable biorefineries are taught. And in the last class, whose live session happened yesterday only, so you can see that I have discussed about the questions around this bio-based fuels, that how biodiesels, bioethanols, biobutanols are produced, and how they also have some advantages or disadvantages also, but still they are much more useful compared to the conventional fuel gas, which will create much pollution to the society, right? So this is it. So you can see here, that is the platform chemicals are used. So there are different types of platform chemicals: succinate acid, xylitol, sorbitol, levulinic acid, lactic acid for fuel. They are used. They can be lignocellulosic biomass. They can be obtained from nature and can be used to production of different type of polymers which are helpful to the nature. So in the last lecture also, it is about the sustainable biorefinery feedstock from food waste. So food waste or municipal solid waste are also can be used as the bio waste, and from which we can produce important materials, carbohydrate rich materials, which is used for the further application, that is for production of bioethanol, biofuel, biogas, and they can be used as in transportation, in electricity, and so on. So they have huge content. So these are the types of food waste we can use. These are the different uses of food waste. Okay, for to balance the bioeconomy. Then this is also the anaerobic ferment. So how these food waste are used? They can do the anaerobic fermentation, then the solvent based thing, and among them anaerobic fermentation is very much important one. So this has been talked details. Then comes the dark fermentation. The fermentation is without presence of light. Okay, then comes the electrofermentation in presence of polarized electrode. Then comes the photofermentation in presence of light, and so on. Okay, so you can see here that uh, succinic acid, fumaric acid, different acid can be used, can be produced from the bioconversion of the carbohydrate-rich products. And carbohydrate-rich products contains glucose, xylose, arabinose, lactose, and sucrose, fructose, etc. Okay, this is a conversion oil-rich waste oil to biodiesel flowchart. Then biodiesel is the fatty acid mixture of methyl ester and ethyl esters. So that has been talked about in detail. This is the food waste and its energy analysis, and that's it. So I have a question for today also, new question. So I would like to go through it because this type of question will come because flow chart is given. Flow chart will be given in the exam, so you have to write the product or the reactant names or the process. Okay, so this is it. So what is the product in this reaction? So natural gas separation happens, it produces butane, and butane dehydrogenation happens and it produces what? The answer is butadiene. Okay, it is not butene, not propene, not even either. So it is the answer is butadiene. Next comes this. So what is the product? You try to answer the question I am giving. I will try to find out what is A and B. I am telling the answer. So what is A? What is A? So what are A and B? So you can see what is A. So this 1245 tetrachlorobenzene, right? React with Na plus OH minus, that is the sodium hydroxide, and produces this 245 TCP, that is 1 minute. So you can see that this is Cl, this is OH, this is Cl, and this is Cl. So this is 1245 tetrachlorobenzene, and it produces reacts with NaOH and it produces 245 tetrachlorophenol. Okay, so this is the A, right? This is the A. And what is B? And it decomposes in presence of exothermic reaction. It produces PCDD. And its structure is huge actually. So let me write. Is Cl here, chlorine is here, then so it's kinds of a symmetric structure, you will understand. You can see that. And It is called B is, this is A and this is B. This is 2378 tetrachlorodibenzo-p-diene, right? So it is 2378 tetrachloro-para-dioxane. Okay, so this is it. Next question. This type of question will come. Okay, this next question is the Scott process. So what is A and P? So in the Scott process, you can see this is a Claus plan, right? This is a Claus process. So Claus process means it will discuss about the sulfur recovery, right? So what is A and what is B? So A is the fuel gas and B is the Scott reactor. Okay, so A is the fuel gas and B is the Scott reactor. Option C, right? Next, what is A and B and C? This is A, B and C. So what are these? So A is, so ammonia reacts with oxygen, produces, so A is nitric acid, that is HNO3. Then B, so ammonia reacts with what, produces HCN, right? So B is methanol or oxygen, okay? And C is ammonia reacts with methanol, produces methylamines. So first produces CH3NH2, one methylamine is added instead of replacing the OH. Then CH3 whole 2 NH2 NH 2 methyl is added. Then tertiary methylamine. Okay, so these are all methylamines. Methylamines. So this is how question will come in the exam. Okay. Next is to explain the overall process for ammonia production. Explain the overall process for ammonia production. So first natural gas is there, right? Natural gas goes for desulfurization to remove the sulfur which is contaminant to the natural gas. Then reforming happens. Okay, then the water gas shift reaction happens. You know the water gas shift reaction. I'm not writing it again. Then CF2 is removed. Then methanation happens. That means methane will produce. Then condensation will happen, where purging also will happen. Purging will lead to the uh, emission of off gases. Then here ammonia synthesis. Finally, the ammonia synthesis. This is NH3 recovery. Okay, so this is the whole process or overall process of ammonia production. Next question is what is A and what is B there. Okay, so you have to see the product. First the product is, so you have to go through the flowchart very carefully because this is how question will come. This is the nitric acid. Okay. So what is the first A? A is the boiler feed water. And product is the, we have seen product is, what is B? Product is nitric acid. So it is not, the answer cannot be nitric acid. So B is weak acid. So boiler feed water and weak acid. Okay. Next is, what is A? What is the pressure A here? You can see this is the high level pressure, compressor zone, right? And the answer is 10 to 15 bar, right? Next, what are A and B here? What are A and B here? So this is the phosphoric acid production reaction, right? So what are A and B here? So when calcium tricalcium phosphate reacts with previously produced phosphoric acid, it produces this structure 3Ca H2PO4 whole 2. This is A, right? And this again, when reacts with sulfuric acid, produces B, that is gypsum or CaSO4. Okay, this is it. Next, in the hemihydrate process of phosphoric acid production, what is A and what is B and what is C? So you have to carefully check the hemihydrate process. So you can see in the hemihydrate process, A is the phosphate rock, right? A is the phosphate rock, right? So we'll write, sorry, A is the phosphate rock, right? Because this is a reactant. Then B. What is B? B is H2SiF6, that is separated. Okay, so it produces H2Fi. So hexafluorosilicic acid is produced, which needs to be separated out in the process. And what is C? What is C? So C is the phosphoric acid. C is the product, very easy. C is the phosphoric acid. 40 to 46% P2O5. Okay. Next question. Repulping process. So in the repulping process, what is A? The answer is gypsum, or rather clear gypsum, you can say. Repulping process, clear gypsum is produced. Next, in the flow diagram of chlorine production, right? Chlorine production. In the diaphragm process, what is B and what is A? So A is chlorine gas, obviously, because on the heat exchanger, chlorine gas is separated out. And B is the reactant. The chlorine process, what is the reactant? Reactant is the NaCl, that is NaCl water, that is the brine solution. So we'll see the A is chlorine gas and B is brine saturation, right? Next, in the Solvay process, what is A? In the Solvay process, what is sent to the Solvay tower? This is, the answer is ammoniated brine. Not only brine, this is ammoniated brine. Okay, so the compound is NaCl plus H2O plus NH3. Okay. Next question is, this is the ethyl benzene production of Monsanto Lummus process. So what is A? So what catalyst is used in the ethyl benzene Monsanto Lummus process? And what is B? Like what type of reactor is called there? The answer is, the catalyst is used in the Monsanto Lummus process is the LCl3, right? And this reaction, the first reactor is called the alkylation reactor, and the second reactor is called the transalkylation reactor. So option B is correct here. Next, this is the ethene oxide plant, right? So what is A, what is B, and what is C? So there are three options are given. So what is that? Which one is A among U absorber, CO2 absorber, CO2 desorber? So first from the reactor, product goes into the U observer section. Okay. So this is U observer is A. Next, it goes into the, if you carefully follow the flow chart, you will see that this is the CO2 absorber. Then comes the desorber. So this is B, CO2 absorber is B and CO2 desorber is C, right? Next is the Lurgi process of pure methanol production, right? And we have seen that in Lurgi process, what is the difference? So here asked that what is the reactor used? Reactor is the multitubular reactor. Okay. Next, the formaldehyde production process. So what are these four column is called? What are these four column? Okay. You think of the reactors. What are the reactors? So first one is the reactor, obviously, right? So first one is the vaporizer. So A is the vaporizer where methanol and steam is going. So A is the vaporizer. Then B is the reactor and waste heat boiler. B is the reactor and waste heat boiler. The third one is the C. C is the absorber and D is the absorption column or distillation column. Sorry. C is the absorption or absorber and D is the distillation column. So if you interchange them, because they in the flowchart they looks like same, right? But if you change the order of them, the C is the distillation column and D is the absorber, if you write that, you will not get the marks. Okay. Next is, what is this? Propene reacts with what produces N-butyldehyde or isobutyldehyde? The answer is obviously the syngas, right? Next is methanol carbonylation reaction. What is the reactor? What is the product? Top product and bottom product, right? What are the top product and bottom product of a methanol carbonylation reaction? What is the top product and bottom product of the methanol carbonylation reaction? So the answer is, first of is the acetic acid. So methanol carbonylation reaction we have seen, it will produce acetic acid first, right? So A is the acetic acid and B is the propionic acid, right? So remember the reaction, right? So what was the reaction? Overall reaction is CH3OH methanol reacts with first the catalyst, that is HI, produces CH3I methyl iodide plus water. Then this methyl iodide produces carbonylation happens. That means it reacts with carbon monoxide, produces CH3COI. Then this CH3COI reacts with water, produces acetic acid, our desired product. And HI is separated again. The catalyst is separated again. Next question, what is A, B, C, D in the hydroformylation reaction of propene? Right? So what is A? A is reactor. So A is reactor. Then B. B is the gas liquid separator. This is B. Then comes the C. C is the stabilizer. C is the stabilizer. And D is the aldehyde distillation. So you can see in the aldehyde distillation, isobutyraldehyde and N-butyraldehyde are separated. And what is A and B here in the low pressure cobalt process? What is A and B here in the low pressure cobalt based process for the direct production of alcohols? So the question is, A is hydrogen rich and B is hydrogen poor. Is it true or false? A is hydrogen rich and B is hydrogen poor. Is it true or false? So in the alkene direct production of alcohols means higher orders alkenes, they are produced A and they will produce the heavy ends products or crude alcohols or aldehyde, where A is the syngas with hydrogen poor and B is the syngas applied with hydrogen rich, right? Okay, so in the first reactor, syngas with low hydrogen is sent, and in the next reactor, hydrogen syngas with rich hydrogen concentration is sent. So I have asked that A is hydrogen rich and B is hydrogen poor. So this is wrong, right? So the answer is false. So that is from my side. I think you have understood all the question answers throughout the sessions, throughout the 12 weeks. My question answer, my assignment sessions, my live sessions were helpful to you for doing your assignments, weekly assignments, and maybe it will be useful for your upcoming exam also. And today's lecture and today's questions, the questions I have discussed at the end will be important because this type of question will come in your exam. Go through the lectures very carefully. Go through the live sessions lectures also very carefully, and obviously the flow sheet question will come, right? They will ask the way I have made the questions today. They will ask the some what is the reactor here, what is the reactant here, what is producing here. So they will blank out that portion and will ask the question. It will be a little bit confusing, but if you practice it, it will not anymore. And so thank you for all the sessions. Whoever has joined or whoever have listened later in the from YouTube. So thank you all of you for joining the classes. Thank you all of you for listening the sessions, and all the very best for your exam. And thank you so much. Goodbye.